Let's take a look at evaluating limits analytically. And this has a variety of different techniques in this lesson. First one is kind of review what we've seen before, and also point out why maybe it's not such a good good technique. Okay. This says use a graphing utility to graph the function and visually estimate the limits. So we've got f of x is equal to x times the absolute value of x minus 3. And we want to find this limit. Limit as x approaches 3 of f of x. And so I'll put it right below it. And then the other one will be the limit x approaches negative 1 of f of x. Well, this is the graphical approach, and sometimes it works, sometimes it doesn't. But it sometimes will give you an answer you think is correct, but it's just close to the real answer. Let's go graph this first. So I'm going to press y equals, and press clear. And we got x. So press the x key, press math, right arrow to num, enter on ABS. And then we got x minus 3. So to x minus 3, and graph. Now I'm zoomed in from previous problem. I'm going to do zoom and choose 6 for Z standard. Like this. We still might zoom out anyway, but I want to show this. Limit as x approaches 3. Well, if I come to x is equal to 3, looks like it's right here. Again, I'm going to zoom in to see it. Not exactly zoom in, but I'm going to choose zoom. And I'll choose Z box. That's one I like. Now press enter on it, and our flashing cursor is in the middle. I'm going to press my up arrow and my left arrow, like that, and I'm going to put it up in the upper left-hand corner where I want to draw a box. So press enter one time, and now I'll do my down arrow and right arrow, and you should see a box drawing. Now this is going to zoom in on just where our box is. So very nice technique for zooming. There we go. Now press enter. Okay. So limit as x approaches 3. So here I am coming from the left side, and I'm approaching x equals 3. Looks like y is going to 0. And here I am from the right side, approaching x equals 3. And again, y is going to 0. So for this particular answer here, this is going to be 0. Now, is it really 0? Well, this might be 0.25 or 0.01. We don't know. We're just kind of guessing. That's what the graphical happens with the graphical method. Now, x approaches negative 1. Now, I've zoomed, did a zoom box, zoomed in. So I'm going to choose zoom and choose number 6 to set my viewing window back. Okay, now I'm going to choose zoom again, and I'll choose Z box, so press enter on it. I'm going to do my up arrow and left arrow. There we go, and up about right there maybe. Press enter one time, and I'll do my down arrow and right arrow. There we go. I won't go down far enough so I can actually see the negative 1, and then I'll press enter. Excuse me. Well, here's negative 1. If I come straight down, it's about right here, which appears to be 1, 2, 3, negative 4, coming from the left and from the right. So again, I just went straight down, and then you can go over to see what your y value is. So I think negative 4 if my eyes aren't getting off. Okay. This would be our answer graphically, and this would be our answer graphically. Well, there's better techniques than that. The next one we're going to take a look at is direct substitution. So let's take a look at an example of that. We've got the limit as x approaches -3 of x squared minus 3x. Okay, with direct substitution, then whatever x value it's approaching, we just want to plug in for x. So we're going to put -3 in for the x. So we got -3 squared minus 3 times -3. -3 squared is 9. -3 times -3 is a positive 9, which gives us 18. And that's our answer. Now in this previous one, now that we've seen direct substitution, let's take a look. If we plug 3 in here, 3 minus 3 is 0. Absolute value of 0 is 0. 0 times anything is 0. So that one checks. If I put -1 in there, -1, -3 is -4. Absolute value of -4 is a positive 4. And then if I put -1 here, I'll have -1 times 4, which gives us -4. So that checks. Always, unless it specifies to use another technique, you should try to use direct substitution because it's so easy. And we'll see some other techniques where the direct substitution doesn't work and we have to use something else. Okay, same instructions. Find the limit. Well, if I plug -1 in for x, I'm going to have 4 times -1 minus 1 over 3 minus a -1. Well, 4 times -1 is -4 minus 1. A negative becomes a positive. So we're going to end up with -5 over 4. And let me change my seat here. There we go. Okay, now the next one really doesn't have a name. It's direct substitution, but it just looks different. It just basically has some algebra you have to do after you do your substitution, besides more than just like adding or subtracting numbers or multiplying them and so forth. There's actually, I guess, two different ways of doing this. Okay, direct substitution. We'll plug 4 in for the x. So I got 1 over 4 plus 3 minus 1 over 3 all over 4, which gives us 1 over 7 minus 1 over 3 all over 4. Okay, now after we do that, like I say, this doesn't really have a name. You had two different techniques of simplifying this. This is a complex fraction. That's where you have a fraction inside of a fraction. And the technique that works all the time is to multiply everything by the LCM of all your inner denominators. Now when I say inner denominators, I'm talking about these fractions inside of the fraction. So my inner denominators would be 7 and 3. So I'm going to multiply everything by the LCM of those, which would be 21. So I take 21 times 1/7 minus 21 times 1/3 and 21 times 4. Well, 21, 7, both divided by 7. 7 divided by 7 is 1. 21 divided by 7 is 3. 3 and 21 both divided by 3. That gives me 1 there. Gives me 7 there. So we're going to have 3 times 1, 3, minus 7 times 1, 7, over 84. Well, 3 minus 7 is -4 over 84. And top and bottom are both divisible by 4, so that gives us -1 over 21. And trying to figure out where to start the next problem. It's another direct substitution, but again, it has a little bit of a twist to it, a simplifying technique. It's probably good here. Okay, limit as x goes to pi over 3 of tangent. Well, we plug in pi over 3 in for x, so I got tangent pi over 3. Now tangent, here's pi over 3, which is 1/2 square root of 3 over 2. Tangent is y over x. So if we come to pi over 3 on our unit circle and look at y over x, we're going to have square root of 3 over 2 all over 1/2. Remember, if you have a single fraction over a single fraction and denominator is the same, you can cancel those. So that's square root of 3 over 1, which gives us square root of 3. We got one more. I think I got room here. One more direct substitution. Another trig one. So we got limit as x goes to 9 of cosecant pi x over 6. Well, direct substitution, we just plug in our number. So we're going to have cosecant of pi times 9 over 6. Now 9 and 6 are both divisible by 3. So 9 divided by 3 is 3. So we got 3 pi. And 6 divided by 3 is 2. So we got 3 pi over 2. Okay, well 3 pi over 2 is down to here. And on our unit circle, this point here will be 0, -1. Now cosecant, remember, is, and this is in terms of our unit circle, cosecant is 1 over y. So we got 1 over, and then the y part, this angle here is 3 pi over 2. So the y part of that point is -1. So we got 1 over -1, or -1 is our answer. Let me save that. And this is, what is this? This is evaluating limits analytically. Okay. So finding limits, and I don't draw a blank that much. T. T-I-C-A-L-Y. And page 1. PDF. There we go. Okay, now that's the last example of direct substitution. Let's see what these other next ones are talking about. Okay, so we got f of x equals x plus 3, and g of x is equal to x squared minus 1. And part A, we want to find the limit as x goes to 2 of f of x. Well, I guess this is direct substitution again, but it's used in a different sense. So we're going to plug 2 into f of x. So we're going to have 2 plus 3, and that gives us 5. Now b, let's be 3. Okay, so we want to plug this in, and got 3. So we got 3 squared minus 1, 9 minus 1, or 8. And I probably meant for those to be the same number, but that's okay. And then we got limit as x goes to 2 of g of f of x. Well, they got a formula for this, and in my view, it's so easy to find this composition that there's no need for you to use the formula. G of x, that's x squared minus 1. So we're going to plug in f in for the x. So remember this, composition of functions. You take your x squared minus 1, and where your x is, you'll put in parentheses. So x squared minus 1. And whatever is inside the parentheses right here, which is f, will go right here. But f, we said, was x plus 3. So we'll put x plus 3 there. Okay. Now for our direct substitution. We'll just put 2 in for the x. So we're going to have 2 plus 3 squared minus 1, which gives us 5 squared minus 1, 25 minus 1, or 24. Now the formula for this says that if the limit, let's see, limit of g of x, oops, got my focus elsewhere. I'm sitting here watching watching TV. Okay, I quit looking at it. So the limit as x goes to c of g of x is equal to L. Then, if you're trying to find a limit as x goes to c of f of g of x, which is what we just did, then that's going to be equal to f of L. And this one was a little bit switched around. See how the g was first and the f was second? But it would be same type of thought process. We know how to find, or hopefully you remember from college algebra, how to find the composition of functions. And if you know how to find the composition of functions, why memorize another formula? Because it's so easy when you plug it in like this that you might as well just do it that way. Now these next ones are a bunch of different properties. So let's show these by example, and most of them pretty well just kind of make sense. So we got limit as x goes to c of f of x is equal to 8, and the limit as x goes to c of g of x is equal to 4. Okay, our first property. Got limit as x goes to c of 5 f of x. Well, whenever you have a number inside and it's times everything that's inside there, inside the brackets, then you can take that number and put it on the outside of the limit. So we can have 5 limit as x goes to c of f of x. So again, if you have a number, you can just factor it out in front. Now, this has got to be 5 times something, or the number times something. You can't have 5 plus. Now, limit as x goes to c of f of x up here is equal to 8. So this becomes 5 times 8, or 40. Now, to me, that property just kind of makes sense. You can factor out a number. This next one. Limit as x goes to c of f of x plus g of x. Well, if you have two functions here added together, and they don't have to be like a function like you might be thinking. You could have x squared plus 3x. So they can just be two terms. Well, if you have addition or subtraction, you can split these up. So you can take the limit as x goes to c of f of x plus the limit as x goes to c of g of x. Now limit as x goes to c of f of x is equal to 8. plus limit as x goes to c of g of x is equal to 4. So 8 plus 4 will give us 12. And I'm going to continue this over here. So C. We got limit. Actually, I'm lying to you. Might as well just do it right underneath here. Okay, limit as x goes to c of f of x times g of x. And it's just then we got division. This just kind of makes sense when you think about it. Because if we were plugging in by direct substitution, plugging into c, whatever number that is, into here, and these are already multiplied together, then, well, you multiply them together after you plugged in your number. So we can split these into two separate limits. So that limit as x goes to c of f of x times the limit as x goes to c of g of x. Well, f of x was equal to 8 times g of x, which is equal to 4, which gives us 32. We multiply those together. And then we got limit as x goes to c of f of x over g of x. Got division. Well, this is kind of like you might expect. We can split them up into limit of f of x over the limit of g of x. So we got limit as x goes to c of f of x over the limit as x goes to c of g of x. Now f of x is 8 over g of x, which is 4. And 8 divided by 4 is 2. So that's our answer. Now this next one. Let's see. Let's see if I have room here. Hopefully I do. We got f of x is equal to x over x squared minus 2x. And let's look at the first one. Limit as x goes to 3 of f of x. Well, I can put f of x in there. So we got limit as x goes to 3 of x over x squared minus 2x. Now, without reading the directions, our first method we should always try to do is direct substitution. Just plug the number in, see if it works. So put 3 in for the x. Put 3 down here. We got 3 squared minus 2 times 3, which gives us 3 over 3 squared is 9 minus 2 times 3 is 6. So that gives us 3 over 3, or gives us 1. So no problem. Now this next one, part B, is going to demonstrate what I call the factor cancel method. Books never have a name for it, so I like to give it a name. And we got limit as x goes to 0, I think. Yeah, 0. Of f of x. Well, I can plug that f of x in there. So we have x over x squared minus 2x. Problem with this is, if I were to do a direct substitution into this, if I put 0 in for x, I'd have 0 squared minus 2 times 0, so I'd end up with a 0 in denominator. You can't have that. So what we're going to do, first step, is factor the top, factor the bottom. So factor the top, factor the bottom. Now the top I can't do anything with, but the bottom is the GCF. So this becomes the limit as x goes to 0 of x over, and the bottom part has an x in common, so x times x minus 2. Then you cancel if possible. Now notice after I factored out the x, down below here I have x times x minus 2. Since this is multiplication, I can cross out these x's. And we got the limit as x goes to 0 of 1 over x minus 2. And now do direct substitution. What was causing us a problem was that x, that extra x down here. So after we get rid of that, we don't have any problem plugging in a number. So if I put 0 in for x, I'm going to have 1 over 0 minus 2, which is equal to negative 1/2. And that's our answer. Let me save that page. And let's look at another example of that. Let me grab a drink here first, though. Okay. 10. Get the limit as x goes to 4 of 2x squared minus 9x plus 4 all over x minus 4. Now as we go through our different methods, direct substitution, if I put 4 in for x, down in the denominator I'll have 4 minus 4. You can't have 0 in the denominator. If at all possible, we avoid the table method because it doesn't give us an exact value, so it gives us an approximation, which sometimes is the answer, sometimes not. The graph is kind of hard to work with. Sometimes when you're looking at the graph and you're trying to see what it's approaching, you can't see it. Well, let's try the factor cancel here. Remember our first step. We want to factor the top, factor the bottom. Well, bottom can't do anything with, but top part is the key number. And it factors as 2x x for 1 minus minus. Now after I factor the top part, I notice that the x minus 4's will drop away. So those are gone. That's step 2, cancel. So now we have limit as x goes to 4 of 2x minus 1. Now what was causing us a problem was that x minus 4 down there, because if I put 4 in for x, it would give 4 minus 4 is 0. It's now gone. So we can now do direct substitution. So I put 4 in for the x, so I got 2 times 4 minus 1, gives us 8 minus 1, or gives us 7. And that's our answer. One more direct substitution. Or I'm not direct. Sorry, one more factor cancel method. Sorry, it's past my bedtime at 6:30. X squared minus 4x minus 21 over x squared minus 9. Well, first thing you should always try to do is direct substitution. If I try to plug in negative 3, I'm going to have negative 3 squared, which is 9, minus 9, which gives us 0. So we're going to try to factor the top, factor the bottom. Top part is the PSD method. The bottom part is the difference 2 squares. So we got limit as x approaches negative 3 of x minus 7 times x plus 3 over x plus 3 times x minus 3. Well, now that we've factored these, we see we can cancel the x plus 3's, so those are gone. So we've got limit as x approaches negative 3 of x minus 7 over x minus 3. Now notice that we don't have a problem anymore. If I put negative 3 in the denominator, negative 3 is not 0. So let's just do direct substitution. So put negative 3 in for the x. So I got negative 3 minus 7 over negative 3 minus 3. That gives us negative 10 over negative 6. The negatives cancel, and then 10/6 becomes 5/3. And that's our answer. Let's look at the conjugate method. So we got limit as x goes to 7 of the square root of x plus 2 minus 3 over x minus 7. Okay, first off, let's just talk this through. Direct substitution. If I put 7 in for x, I'm going to have 7 minus 7 denominator, which gives me 0. Can't have that. Table methods, probably last resort. Graphical is not very good. Factor cancel method. Well, I can't factor the top or the bottom, so I can't do that. Now, specifically, notice how there's radicals involved. So when you have radicals involved, that's where you can use this conjugate method. Okay, what we do is multiply the top and bottom of the fraction, numerator to denominator, by the conjugate of the top. So for this problem here, we got square root of x plus 2 minus 3 over x minus 7. Conjugate of the top. If you remember what conjugate is, the first part and the last part are the same. So this will be square root of x plus 2, and this will be 3. The sign in the middle changes. This is negative, so this becomes positive. And whatever you multiply by the top, you have to multiply by the bottom. Like that. Now the neat part about conjugates is when I multiply them together, all I have to do is multiply your first parts together and your last parts. So I'll take square root of x plus 2 times square root of x plus 2. That gives us x plus 2. And then we got negative 3 times positive 3, which gives us negative 9. Now the bottom part we don't actually multiply together. We just put them next to each other. You don't want to use distributive property on that, because you're hoping that x minus 7 will disappear, because that's what's causing me a problem. I'll do a little bit of simplifying on top. 2 minus 9 is negative 7, so we got x minus 7 over x minus 7 times square root of x plus 2 plus 3. Now notice after I've multiplied by the conjugate, I got x minus 7 here and x minus 7 here. Well, those are going to cancel. Excuse me. So then we got limit as x goes to 7 of 1 over square root of x plus 2 plus 3. And now we can do our direct substitution. If I put 7 in for x, it's okay. So I have 1 over square root of 7 plus 2, then plus 3. Which gives me 1 over square root of 9 plus 3. And square root of 9 is 3, so we got 3 plus 3, which would give us 1/6. And that's our answer. And that's the conjugate method. I think I only have one example of that here, yes. So let me go ahead and save this. And let's look at our next type. It's not really a method, it's more of a type. Okay, we got the limit as x goes to 0 of 1 over x plus 6 minus 1 over 6 all over x. Yeah. Okay, now the direct substitution. If I put 0 in for x, I'm going to have a 0 in denominator. I can't have that. Well, there's no special technique here, but there's some algebraic techniques we have to use. You notice how we have a complex fraction inside of a fraction? Well, we need to get rid of the complex fraction. We need to multiply everything by the LCM of all our inner denominators, which are the 6 times x plus 6. So our LCM will be 6 times x plus 6. And we'll multiply that times our first fraction. And we'll multiply that times our second fraction. And then we'll multiply it times the x that's downstairs. Can't forget it. Okay. Here these x plus 6's cancel here. Over here these 6's cancel. And then we got limit as x goes to 0. We got 6 times 1, which gives us 6, minus 1 times x plus 6. And down below, x times 6 is 6x times x plus 6. I don't want to actually multiply it through down below, because we're hoping something will cancel. Up on top, we got negative 1 times x. That gives us negative x. Negative 1 times 6 gives us negative 6. Then we got limit as x goes to 0. The 6 minus 6 cancels away, and you got negative x over 6x times x plus 6. Now notice down below we have 6 times x plus 6. Everything's multiplication. And we got an x up here. So I can cancel this x with this x here. The reason I can do that is because this x down here is multiplied by the 6 and by the x plus 6. So then we got limit as x goes to 0 of negative 1 over 6 times x plus 6. Now after we've done some basic algebra, we can plug in our 0 for the x. So this now becomes negative 1 over 6 times 0 plus 6. 0 plus 6 is 6, times 6 is 36. We got negative 1 over 36. The next one is some simplifying too. Let me grab a drink before I tackle this. A pop, that is. I don't expect I could probably do, well, I don't drink anymore at all, but I don't expect I could probably do math intoxicated. I don't think I ever tried, but let's see. Got x plus delta x squared plus 2 times x plus delta x minus x squared plus 2x all over delta x. Okay, well, we want to simplify this and see what happens. Look down to here, so I have a little bit of room to work. Okay, so we got limit as delta x goes to 0 of x plus delta x times x plus delta x. That's what that squared means. Plus 2 times x is 2x, 2 times delta x is 2 delta x. If you have a negative out in front of your parentheses, it flips the sign of everything inside, so it becomes a negative x squared minus 2x all over delta x. Now this 2x right here is going to cancel with this negative 2x, so I can go ahead and drop those. And if I multiply these together, I'm going to get x squared plus x delta x plus x delta x plus delta x squared. And then this carries down. So we've got plus 2 delta x minus x squared all over delta x. Well, the x squared here cancels with this negative x squared. So we have the limit as delta x goes to 0 And x delta x plus x delta x, since these are the same, you add the numbers that are in front of them. So this is 2x delta x plus delta x squared plus 2 delta x all over delta x. Okay, just basic algebra up to that point. Now you notice up on top, everything has a delta x in it. So I'm going to factor out a delta x. And then that'll give us 2x plus delta x plus 2 over delta x. And now, after we factored that out, we have delta x times this. So since that's multiplication up there, this delta x will cancel with this delta x. And you have the limit as delta x goes to 0 of 2x plus delta x plus 2. Original problem was that delta x that was downstairs, because we can't plug 0 in, we can't have a 0 in denominator. That's gone now, so we can plug in 0 for delta x. So this becomes 2x plus 0 plus 2, which gives us 2x plus 2. And that's our answer. Now this particular problem here, we're going to see this more when covering a derivative. So it's just some basic algebra. Now the next problems are trig ones, and there's some special formulas that we'll take a look at. So special formulas. Our first one is the limit as x goes to 0 of sine x over x is equal to 1. And then the limit as x goes to 0 of 1 minus cosine x over x is equal to 0. Then our last one, the limit as x goes to 0 of 1 plus x to the 1 over x power is equal to e. So let's take a look at some problems dealing with that. Okay, got the limit as x goes to 0 of 9 over x minus 9 cosine x over x. Well, the only one that's even a possibility is the second one, because it has cosine in it. Well, this one has a single fraction, so let's try to merge these together, see if that helps us. So I'm going to take these and merge them together. The denominators are the same, so all I have to do is put top parts together. And that's closer. There's an x, here's a cosine. I notice that these both have a 9 in common. Well, I can factor out a 9. That gives me 1 minus cosine x over x. We talked about this property earlier on. If you got 9 times something, multiplication, then this is a number. You can take that number and put it out in front of the limit. Now, if that was a x, we can't pull that out in front of the limit. But numbers we can freely take in and out. And then we're left with 1 minus cosine x over x, which the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. So this now becomes 9 times 0, or 0. Let's take a look at another trig one. And take another drink. I need to quit drinking so much pop. Be up all night. Okay. So we got limit as theta goes to 0 of 1 over theta cosecant theta. Don't have cosecant over here, but cosecant I know is 1 over sine. So I can rewrite this. Limit as theta goes to 0 of 1 over theta times 1 over sine theta. Now, we can, to get rid of this fraction inside of a fraction, we can multiply top and bottom by sine. And if we do that, we'll get sine theta. And multiplying this by sine would cause this to cancel. So we'd have sine theta over theta. Which sine theta over theta would give us 1. So that's our answer. And don't have room for this one. Oh well, let me save this. There we go. And our next one is 17. So we got limit as x goes to 0 of 5 over x cotangent squared x. Okay, well, we don't have our formulas up anymore, but we had one that had a sine in it and one that had a cosine in it. So probably we want to convert this cotangent to cosine and sines. So this would be a limit as x goes to 0 of 5 over x times cosine or cotangent is equal to cosine over sine, and cotangent squared will be cosine squared over sine squared. Now whenever you have a single fraction down here, you can flip it and multiply times your top part. So this becomes 5 sine squared over x cosine squared. So then we got limit as x goes to 0. And what that means is we got 5 sine x over x cosine x cosine x. We can split them apart like that. Now one of our formulas says sine x over x. So we're going to rearrange this. Limit as x goes to 0 of sine x times 5 times sine x over x times cosine x times cosine x. Because multiplication is commutative, so you can flip them around. And let me continue it up here. Now, one of our properties says if you got multiplication like this, you can split them into two separate limits. So we got limit, as x goes to 0 of sine x over x times the limit as x goes to 0 of 5. Try to write a little bit more legible. 5 sine x over cosine squared. Okay. Well, limit as x approaches 0 of sine x over x. This is one of our special formulas. That's equal to 1. And this over here, if I put 0 in, I got 5 sine 0 over cosine squared 0. Now, sine 0 is 0. So we're going to have 5 times 0 is 0, and then 0 divided by anything is 0. Assuming this is not 0, which it is, and it's 1. And then 1 squared is 1. So we got 0 over 1, 0. So we got 1 times 0, which then gives us 0. And that's our answer. Now the next one doesn't use the those three formulas, but it is a technique that you may not have seen before. So let's talk about it. Limit as x goes to 0 of 5 e to the 2x minus 1 over e to the x minus 1. Now if I were to plug 0 in, we'd have e to the 0, and anything to the 0 power is 1. So this would be 1 minus 1 or 0. We can't have a 0 in the denominator. Let's look at this top part here, and I'll do it over here on the side. We got e to the 2x minus 1. Back in college algebra, we covered difference of two squares, where you had two terms with a minus between it. Well, it doesn't have to be terms. It can actually be anything. So if you got two anythings with minus between them, you could try to rewrite it as something squared minus something else squared. Now this would be 1. 1 times 1 gives you 1. And this would be e to the x. Going backwards, if you raise one exponent to another exponent, you multiply them together. So x times 2 would give you 2x. Now we were able to write this as something squared minus something else squared. The difference of two squares says we take what's inside our first set of parentheses, we add what's in our last, and we take what's inside our first and we subtract what's in our last. So it factors this way. So let's go back to our limit here. Now we have a number, and we know already if we've got a number like that, 5 times this, we can take the 5 and put it out in front. And not even worry about it. Top part factors as e to the x plus 1 over, or times e to the x minus 1, all over e to the x minus 1. Okay, after I factored the top part, I see I can cancel something. The e to the x minus 1, e to the x minus 1. So those are going to cancel. And we have 5 times the limit as x goes to 0 of e to the x plus 1. And now it's okay for us to plug in 0. Now notice, when I drop the limit and plug 0 in, I'm going to have e to the 0 plus 1, and I have to put parentheses around them, because this is going to be 5 times all of that. Well, e to the 0 is 1, so we've got 1 plus 1, which gives us 2, and then 5 times 2 gives us 10. And that's our answer. I don't think I have room for this next one here. I might, but let me go ahead and save this page and start a new one. There we go. Okay, number 19. We've got f of x is equal to square root of x minus 3. And we want to find this formula right here. This is actually a formula we'll see when we get to the derivative. In order to use this formula, the delta x doesn't matter, but we need to find f of x, which we're given. And then we need to find f of x plus delta x. This is like evaluating a function. So we got f of x plus delta x. You're going to take your original function here, and wherever you have an x, you'll put in parentheses. So you have parentheses there, minus 3. Now whatever is inside the parentheses over here is what you're going to put inside the parentheses right here. So this becomes x plus delta x. And I can get rid of those parentheses now, and we got x plus delta x minus 3. Okay, now what they're wanting us to find, they want us to find the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Well, let's plug in what we've just identified. We said f of x plus delta x is this right here. So this is square root of x plus delta x minus 3 minus f of x, which was square root of x minus 3, all over delta x. Now we want to find this limit, but if I plug 0 in for delta x, I'm going to have a 0 in denominator. Can't have that. Well, hopefully this looks familiar. This is the conjugate method, because we have radicals up on top, don't we? So the conjugate method, we're going to multiply top and bottom by the conjugate of the top. So we've got x plus delta x minus 3 minus square root of x minus 3 all over delta x. Okay, conjugate. Remember the conjugate, the first part and the last part are the same. So this will be the square root of x plus delta x minus 3, and this will be the square root of x minus 3. But the sign in the middle changes. This is negative, so this will be positive. And wherever you multiply by the top, you have to multiply by the bottom. So that's x plus delta x minus 3 plus square root of x minus 3. Okay, so then we got limit as delta x goes to 0. Now, conjugates are nice. All you have to do is multiply your first parts together. So we're going to multiply the square root of x plus delta x minus 3 times the square root of x plus delta x minus 3. Since the radicals are the same, the radical will disappear, and you'll just be left with x plus delta x minus 3. Negative times a positive is negative. And square root of x minus 3 times square root of x minus 3 is x minus 3. Now notice I put parentheses around it. This negative has to flip sign about everything that follows it. And what's down below we don't actually multiply together. We just put it next to each other. Because we're hoping that delta x will disappear. Okay. So back up on top. We got x plus delta x minus 3. Negative in front of your parentheses flips the sign of everything inside. So we got negative x plus 3 over delta x times square root of x plus delta x minus 3 plus the square root of x minus 3. Okay, up on top, we got x minus x. Those are going to cancel. We have negative 3 plus 3. Those are going to cancel. So we're left with, what are we left with? Delta x up on top. Then down below we got delta x times square root of x plus delta x minus 3 plus square root of x minus 3. Now you notice down below it's delta x times this. Since this is multiplication down here, these delta x's is going to cancel. And we got the limit as delta x goes to 0 of 1 over square root of x plus delta x minus 3. You know, as weird as it seems, we're still just doing algebra. We haven't even got to the calculus part yet. Calculus part's coming up next. We're going to plug 0 in for delta x. So this becomes 1 over square root of x plus 0 minus 3 plus square root of x minus 3. Okay, that's our calculus step. Okay, back to algebra. This becomes 1. This 0 drops away, so we got square root of x minus 3 plus square root of x minus 3. Remember, if your radicals are the same like that, you can add or subtract the numbers that are out in front. In this case, I have an invisible 1 here plus invisible 1. So that gives me 2 square root of x minus 3. And if I had to guess, they'd probably leave their answer to that form. Where in intermediate algebra they said always get rid of the radical down in your denominator, oftentimes in calculus we find it easier to leave it down there. So let me save that. And we'll go to our next problem. Now I'm going to actually, I could write the theorem up, but I like to do this by example for the squeeze theorem, because I think it makes more sense if you see it. Okay, so we got use the squeeze theorem to find the limit. So limit as x approaches c of f of x, and they're specifically telling us c is equal to 0. Then we got 3 minus absolute value of x is less than or equal to f of x is less than or equal to 3 plus absolute value of x. Now we have no clue what f of x looks like, so it's kind of weird that we're going to be able to find the limit of it. Let's look at this 3 minus absolute value of x. Remember what absolute value of x is from college algebra? That's your v shape, isn't it? Negative flips it upside down, reflects it, and then the plus 3 here moves it up 3. So we're going to be taking a look at 1, 2, 3. So it's shifted up 3 and it's flipped upside down. So this is 3 minus absolute value of x. The other one is 3 plus absolute value of x. So it's shifted up 3 again, but it's still v-shaped going up like that. So this is 3 plus the absolute value of x. Now let's pretend that our graph looks like this. Now, what we're going to do is see how this graph is between these two. That's what this says right here. That f of x is between 3 minus absolute value of x and 3 plus absolute value of x. Well, let's take the look at the limit as x goes to 0 of 3 minus absolute value of x. That's this bottom one. Well, if I use a direct substitution, put 0 in for that, I got 3 minus absolute value of 0, which gives me 3. And then, you got limit as x goes to 0 of 3 plus absolute value of x. Well, if I put 0 in for x, I got 3 plus absolute value of 0, which gives us 3. Okay, now think about what we're doing here. Let me write this down, because we're ready to write our answer. This f of x, the red, is trapped between these. Squeezed between them. So, and if the limit of each one of these goes to 3, and this is trapped exactly in between them, well, in between them or equal to, then your limit is going to be the same as these. So the limit of our function is going to be 3. So that's a squeeze theorem. It's a very simple concept once you look at it graphically and see it. Sometimes coming up with these functions, 3 minus absolute value of x and 3 plus absolute value of x, assuming they don't give them to you, that's kind of the tricky part. Let me save this. I think that was the last problem. Yeah, it was. So let me stop the recorders. There we go. Let's stop the other recorder.